All right, so this, yeah, we were right here. So this is this is actually getting to what's called the hydraulic gradient. But before we get to that, let's talk about the hydraulic head, which is simply what the water table level is. Usually we talk about above sea level just to make everything clear. Like for example, for A here, the water table head is 440 meters above sea level. And of course, the aquifer will flow towards B because B is lower, right? I mean, water always flows downhill, and so at B, the water, the hydraulic head is at 415 meters above sea level, and so the difference between them is well, that's how we calculate the gradient. So the gradient is the what we call. You might remember this from talking about slopes when you did algebra. You talk, anyhow, it's the rise over the run. All right, so that's basically what we're going to do to work out this thing called the hydraulic gradient. All right, so it's going to be the difference between the height at A and the height at B, and then you divide by the distance between A and B. All right, so here let's look at an example of that. Hold on, let's switch to the textbook. I think I have an example of that. Sorry, there we go. Right, so right here, there's a nice example of calculating the gradient. And the reason that we're doing this has to do with what's called Darcy's law. We'll get to that in just a second. But so it's the height at A. With respect to any, usually sea level is the easiest thing to use. So the height at A minus the height at B, and then divided by the distance between them. All right, and so the units all have to be the same. So the height of the water table at A is in meters. The height of the water table at B is in meters, and then the distance between them is also in meters. Just make sure that everything's in the correct units. So the gradient is basically a unitless number. So notice it says the groundwater flow rate is proportional to the hydraulic gradient. So that's part of, or that led to this idea of Darcy's law. So Darcy was as it says right here, he was a French engineer. Lived more than 175 years ago. He came up with this formula that so the groundwater flow rate, right? You might need to know that is equal to what's called the hydraulic conductivity. How easily the water flows through the aquifer times the cross-sectional area. So the cross-sectional area would be like if I just took a slice, somewhere in the middle of this, perpendicular to the direction of the water flow. That's what's called the cross-sectional area. And then you multiply by the hydraulic gradient. That'll give you the rate of water flow. All right, so let's go back to our slides. I just wanted to show you pictures of that, or a little bit better pictures of that. All right, so the only thing you remotely have to calculate would be the gradient, and it's not too bad. It's just the difference between A and B divided by the distance between them, and make sure they're all in the same units. All right, so there's Darcy's law, and we just encountered it. The groundwater flow rate is related to what's called the hydraulic. So you would be given these numbers, right? The hydraulic conductivity and the cross-sectional area, and probably have to calculate the gradient. All right, I'll look at it and see if there's something where we need to do this. If so, I'll make an example. I'll do an example, a full-blown example. All right, so the flowing groundwater can alter and change the features of the surface, as it says. So this idea of land subsidence, and the formation of caves and caverns and even sinkholes. Okay, so remember, there's these aquifers all over the planet. There's actually a giant one in the western United States that extends over many, many states. Let's see if I can remember the name of it. Hold on, let me look at the textbook. It'll probably have that aquifer. Let's see if I can find it. I don't see it right there. Groundwater. So this is the land subsistence. There's Darcy's Law. There's a nice example of Darcy's Law. All right. Anyhow, all right. We'll get to this Leaning Tower of Pisa stuff. All right. So yeah, I thought I'd be able to find the name of that aquifer. Anyhow, it's the largest one in the United States. All right. So how does this land subsistence come into play? What is that all about? So when you remove like huge portions of the groundwater, like they did, let's see, this was in California, and so the groundwater will it was pumped out for irrigation purposes. Remember that we grow a lot of vegetables and so forth. A lot of produce comes from California, and so the water originally, back in the 1940s and 50s, was pumped out of these aquifers without regard to what it was doing to the land, and so the land actually. This is a good example of land's subsistence. It's where these aquifers are made on these sandy sediments and clay. Of course, the clay. So basically, when you pump it out, it causes the land to kind of to shrivel, to sink and shrivel. And of course, that's not a good thing. If you're continuing you want to continue to use the land, as the water is pumped out of the ground, the fine grains of clay particles become compacted and cause the land surface to lower. And it can look, that's what this picture is showing is where the land was in 1955 and 1925. It used to be way up here, and so now it's down to right here in 1977. And so it's, I think they actually solved this problem, although, there's nothing you can do to what happened to the land, once this subsistence, the land subsistence is, once you damage the land, there's really not a lot you can do. All right, and then there's some other things that groundwater can do, and in forming caves and caverns, and so and this isn't just from humans, right? There's always been carbon dioxide in the air, right? And going back since the first volcano exploded on Earth, which you're talking about billions of years ago, there's always been carbon dioxide, and since what happens is the rain, the water will interact with this carbon dioxide, and it will turn into the water will turn into a very very weak acid called carbonic acid, and so that carbon it is acidic, right? It is slightly acidic, and what that does is with certain rocks like limestone, it's specifically limestone, as a matter of fact. It tends to dissolve the limestone, with much more than normal rainwater. The acid rain, or sometimes it's called acid rain, but it's really carbonic acid. Will cause these things to cause if there's this limestone underground, it will slowly seep away, because the acid will eat at it, will eat at the limestone, and that's how some of these underground caves and caverns will appear. So this is a good example. Groundwater has carved out these huge, in some cases, really large caves. I'll give you a really good example that I've personally visited many, many times. If you've ever gone up and down Interstate 65, it's between Alabama and Indiana. So when you do that, you cross from Indiana, you cross down into Kentucky, and just below, well, it's not just below, but several miles south of Louisville, off of I-65, there's this gigantic cave, and in fact, they think it's the biggest cave in the world. It's called Mammoth Cave, and this is kind of how Mammoth Cave came into being. Is the groundwater has caused the limestone to kind of erode away, flow away with the aquifer, with the movement of the water, and left these gigantic. It's incredible the size of this cave. They have like tours and stuff like that, and it's kind of cool. You get to go in there and they turn off all the lights so that you can see exactly how dark it is for just a moment or two. And they don't take you too far down into the cave, but even in the middle of the summer, it can be hot as anything, 90 degrees or something at the surface, and then as soon as you drop down into that cave, it's cool as I think it gets down to like 50 degrees or something like that. At any rate, so that's just one example of the cave. There's other ones, Carlsbad Caverns. What else? All right. Anyhow, anytime that the carbonic acid takes away some of the limestone and leaves these huge caverns, that's what we're talking about. The sinkholes are so imagine like these things. The rock right above this is, let's say it's rather weak, and let's say you had a huge hole right here, and all of a sudden the rock breaks, and you see this giant funnel shape. That's basically what a sinkhole is. It's just where the ground has weakened enough to fall into the cave underneath. All right, so that's and you hear about sinkholes, swallowing cars. I think Florida seems to have a lot of sinkholes. I mean, they're not the only place, but you watch the news sometimes. There'll be somebody who they lost their car because of a sinkhole. I mean, it's not funny. I shouldn't laugh, but because that's their property, obviously. All right. So anyhow, I'm not exactly sure why that happens so much in Florida. All right. It might have to, actually, now that I think about it, it might have to do with this, pulling out the groundwater that I think that happened a lot down in Florida. All right. Next is these. This is actually a region in Yugoslavia called the Kars region. And it's characterized by these beautiful soft rolling hills or these sharp and rugged surfaces. So the Kars region, let's see if we can get a picture of that, are areas where sinkholes, caves, and caverns tend to define the land surface. All right, let's go to our text. Oh, this is a good picture of it. Actually, that answers this question. What kind of formation is this? Of course, that's one of these karst regions. But here, let's see if I can find a better picture of it in our textbook. Here, not the Leaning Tower of Pisa. All right, it's right. Right. I guess that was the same picture. All right. Well. All right. I got this. All right, here's another picture from our textbook. This is just characterized by some rolling hills, but you can see, like, even as time has gone on, the vegetation has grown in this area. Here, and of course, this is another one. This is, of course, the way these karst regions look in